At this point in the course, we've been talking a lot about fugacity, and I just wanted to take a minute here to just recap sort of where we are in terms of our use of fugacity to talk about phase equilibrium. Remember, at equilibrium, we know that for a given component, say component I, the fugacity of that component is going to be equal in all phases that are in equilibrium with one another, whether it is a vapor phase in equilibrium with a liquid, or two liquid phases in equilibrium, or a vapor that's in equilibrium with two separate liquid phases, so on and so forth. The guiding principle is that at equilibrium, the fugacity for a given component is the same in every single phase that is in equilibrium with each other. So then the question becomes, how do we start to do something with this fugacity and something that relates things back to measurable quantities? Right, and so we've talked about a couple different ways of doing this, and I just wanted to refresh or review that here. The most straightforward example we've talked about is the situation for the vapor phase, right, where we said that the fugacity of some component I in the vapor phase is equal to the mole fraction multiplied by a fugacity coefficient times the pressure. And this is the general expression we're going to use for the fugacity of a vapor. It means that if we have an ideal gas, right, that the fugacity is simply equal to the partial pressure of that component in the gas mixture. In other words, the fugacity coefficient goes to unity. Right, and remember that this fugacity coefficient is calculated using an equation of state. Right, so those are things you talked more about in Thermo 1, right, when you were talking about describing real gas behavior. But equations of state are used to calculate fugacity coefficients, and that's what we're using here in terms of phi for the vapor phase fugacity. Now, if we look to the liquid side of things, which is what we've also thought about, though we're going to consider solids as well at some point here, but as we look toward liquids, right, things get a little bit more complicated here. We have a couple different things that we can do. Remember that we can still use a fugacity coefficient for the fugacity of component I in the liquid phase, right? So we always have this option available to us. It's exactly the same form that we have for the vapor phase fugacity, but now the way that we're interpreting the fugacity coefficient for the liquid is different, right? Because we would need to be doing the calculations using the equation of state for the liquid as opposed to the vapor. But we always have this option available to us to use a fugacity coefficient in the expression for the liquid phase fugacity, right? And we said that if we do this, right, we can come up with an expression that we called the phi-phi method, where at equilibrium, we set the two fugacities equal to each other, the pressure cancels out, and we end up with a situation where we get something that looks like this, and we'll just put vapor and liquid up on the superscripts for the fugacity coefficient here, just to remind ourselves that we would have to evaluate those fugacity coefficients at the corresponding liquid or vapor conditions that are in equilibrium with each other. Interestingly, also, we could look at this and recognize that this means that our K value that we've talked about, which is defined as just yi divided by xi, right, is simply going to be equal to the ratio of the fugacity coefficients for the liquid phase divided by that of the vapor phase. Right, and so if we have expressions for the fugacity coefficients for the liquid and the vapor, then we could also come up with an expression for the K value in terms of the phi-phi method that we've talked about. I'll just make this a little bit clearer that that's an I. Right, so that's the phi-phi method. And the phi-phi method highlights the fact that we can use a fugacity coefficient for the vapor phase or for the condensed phases. Now, sometimes we don't want to use a fugacity coefficient. We don't want to use the phi-phi method. Sometimes we don't have parameters, or the equation of state or the mixing rules don't work well to give us fugacity coefficients for our system in both the vapor and the liquid phase. So we have other options, right? We talked about using activity coefficients. And to do this, we said we defined the pure component standard state as being one where the fugacity is given as the mole fraction of component I times an activity coefficient times the fugacity of pure component I in the liquid phase. Right? And this pure component standard state comes from the fact that we're using the pure fugacity. Right? And we said that we can, expand this out. We used the 3 different ratios back in class period number 3, but we said that under the majority of conditions, this simplifies down to something that looks a little bit closer to Raoult's law, now with an activity coefficient in place. And for this to be true, we need to be treating the vapor phase as ideal, at least at the saturation conditions, and we need to be at moderate enough pressures that the Poynting factor has gone to unity. But in this case, the pure component standard state gives us an expression for the fugacity, and we said that this pure component standard state is defined such that as the composition of a particular component goes to unity, or as we go to a pure component, then the activity coefficient goes to 1 due to the fact that we know ultimately that pure component systems are by definition ideal liquids or ideal solutions. Or another way of saying that, right, is that for an ideal solution, the activity coefficient goes to 1, and we end up simply with this type of relationship, or we can put that again in terms of PI sat, as we've done, for example, in Raoult's law. So pure component standard state is another way that we can evaluate things. Remember that the activity coefficient here is going to be calculated using an activity model. And we've seen some examples of activity models out there. We've used a few of them on the homework. We've used some of them in Aspen, right? We use activity models to calculate activity coefficients, which is different from equations of state, which are used to calculate fugacity coefficients. All right, so now what we're going to do moving forward is we're going to come up with a third option for how we deal with the liquid phase fugacity. We're going to call this the dilute solution standard state, or DSS. And in this case, what we're going to do is we're going to come in and say that we have a situation where we have fugacity for the liquid phase. And now instead of using the pure fugacity of the liquid for component I as this proportionality factor, we're going to use the Henry's law constant. And so we're going to have to redefine things here a little bit. But again, instead of using the pure component fugacity, we're going to use a Henry's law constant, and we have to redefine for the dilute solution standard state how we're going to look at the activity coefficient. So we're using superscript h's here to remind ourselves that this is the dilute solution standard state. And of course, if our system is ideal, right? If we have an ideal solution, our activity coefficient still goes to 1. And we end up recovering an expression that should look familiar in terms of being Henry's law, right? So we get mole fraction times the Henry's law constant gives us the fugacity of an ideal solution in the dilute solution standard state. And if we had an ideal vapor involved in that, we could say that then the fugacity of the vapor phase, or the partial pressure of I in the vapor phase, is equal to xi times kih. And ultimately, we'd get this relationship that we often see, where at the end of the day, we get a situation where for a given partial pressure of component I, if we divide by the Henry's law constant, right, that gives us a measure of how much component I ends up in the liquid phase, and that's useful if we're, for example, thinking about oxygen solubility in water and we have a Henry's law constant and the system is relatively ideal. We can use Henry's law. At the same time, we're going to recognize that if we move out of the range where ideal solution applies, we can still use the Henry's law constant, but now we need the dilute solution standard state activity coefficient. And different from the pure component standard state, we're going to say that in the limit where xi goes to 0, that's the place now where the dilute solution standard state activity coefficient goes to 1. Right, and so this is similar to but opposite of what we had for the pure component standard state. The pure component standard state ideality occurs as we go toward x sub I equals 1, or as the component becomes pure, which is why we call it the pure component standard state. In the dilute solution standard state, the activity coefficient goes to unity as the solution becomes infinitely dilute in that particular component. And that's why, again, in terms of oxygen sorption in water, we use Henry's law, and you've probably never seen an activity coefficient in Henry's law before, because oxygen solubility in water is so low that the system can be considered ideal. And again, in the dilute solution standard state, this sets up a situation where the dilute solution standard state activity coefficient will go to unity. So we're going to talk more about how we work with the dilute solution standard state and how we do some problems associated with that. But just really want to highlight here the different ways that we have to deal with fugacity, right? So we can deal with fugacity in the vapor phase using a fugacity coefficient and equations of state. We can do the same thing for the liquid phase, right? We can use fugacity coefficients and equations of state to describe the fugacity there. Or we can come in and use the pure component standard state. Or now we can come in and use the dilute solution standard state. And so for the liquid phase, for fugacities, we have 3 different ways that we can approach expressing or connecting the liquid phase fugacity back to measurable properties. And depending on the circumstances, the data, what's convenient for us, it's likely that one of these 3 options will be preferable for any given system. But ultimately, at the end of the day, this is the approach that we're going to take to dealing with both the vapor and liquid phase fugacities. So I'd like everybody to take some time to review this, right? Because we want to be thinking about how we connect fugacity to measurables. And because we're starting to spread out the web of what we're doing here, we need to keep all of these options in mind so that when we're presented with a new problem, we're able to pick the option that is best suited for the specific problem that's being presented to us. So, brief overview here in terms of thinking about fugacity and a review of how we do that, at least for vapor and liquid phases. We'll go ahead and wrap things up with this video here.